Okay, so, let me get to the PowerPoint. All right, so if I remember correctly, this is where we stopped the last time. I think I did the first example. So now I'm going to move on to the next example. So the next example says, ammonium sulfate, a common fertilizer used by gardeners, is produced commercially by passing aqueous ammonia into an aqueous solution that is, I'm sorry, gaseous ammonia into an aqueous solution that is 65% sulfuric acid by mass and has a density of 1.55 grams per mil. So the question is asking, how many milliliters of this sulfuric acid solution are required to convert 1.00 kilograms of ammonia to ammonium sulfate? So again, I'm going to copy and paste this onto Word. Okay, so that's a question. So again, what would be the first step in solving this problem? Anybody? What would be the very first thing you would do? Yes, ma'am.
Right.
Okay, so what would be the reactants in this reaction? Based on the information provided in the question, what would be the reactants? Ammonia, which is NH3, and that will react with H2SO4. Okay, so those are the reactants, and then what would be the product? There's only one product, ammonium sulfate, and that's the formula, NH4, 2SO4. And then we need to balance this equation. So how would you go about balancing this equation? Well, this should be easy.
Hello, Professor.
Mm-hmm.
It's 2, 1, 1.
Very good. All right, thank you. Okay, so that's the first thing you need, a balanced equation, right? So the question gives you the mass of ammonia sulfate that you're trying to get, right? And the question is asking for the volume of the sulfuric acid that is required to make that much, right? The question also gives you two other pieces of information. It gives you the percentage of sulfuric acid in the solution, and it also gives you the density of the solution. So let's see how we can use all of that, put them together to get the answer, right? So what I would do is start off with the 1.00 kilograms of ammonium sulfate, right? And what I would focus on, starting from here, is how do I get from the mass of the sulfate given in kilograms to moles, right? So the first thing I would do is multiply this by, I would convert from kilograms to grams. So that means I'll multiply this by 1,000 grams of ammonium sulfate as a numerator. Two erases here. So 1,000 grams of ammonium sulfate over 1 kilograms of ammonium sulfate, right? And then the next step would be to convert from grams to moles, right? So that means I need to figure out what the molar mass of ammonium sulfate is. So I'm going to put 1 mole of NH4, 2SO4 above as a numerator, and then I would have to calculate the molar mass of, you know what? I'm too lazy today, so I'm going to cheat on it. And what I'm going to do is I'm going to use my trusty old molar mass calculator. All right, so this is what I oftentimes use when I'm calculating the molar mass of anything. Unfortunately for you guys, you won't have access to this, so kind of sucks for you guys.
Thank you for this. It's like maybe you treat the font size will take last second.
Okay, so let me make sure I put in the formula right. NH4 2SO4. All right, so the molar mass of ammonium sulfate is 132.14. So let me go back to the Word document. So 132.14 would be molar mass of ammonium sulfate. All right. So in terms of cancellation of units, that would go with that. That would go with that. And then now the next step would be to go from moles of sulfuric acid, moles of ammonium sulfate to moles of sulfuric acid, all right? And based on the balance equation here, it's a 1-to-1 mole ratio between the two. So basically the next conversion factor is going to be 1 mole of NH4 to SO4 below and above will be 1 mole of ammonia. All right. So that's as far as that is concerned. Okay, I'm sorry, not ammonia, sulfuric acid. You always slipping up somewhere. This should be sulfuric acid. My bad. So sulfuric acid, H2SO4. All right. So far we have the moles of sulfuric acid when this cancels out with that. Okay. So the next step is how do we get from, remember now, the aim is to get to milliliters of sulfuric acid. They gave us the concentration of the solution in terms of percentage, right? And they gave you the density of the solution and they're asking for the volume in milliliters. So I'm just going to continue down here, right? And what I'm going to do is I'm going to multiply this by this conversion factor, which represents the molar mass of sulfuric acid. So here we're going to have 1 mole of H2SO4. And the molar mass, again, I'm going to go to my trusty molar mass calculator. So this time I'm going to put calculate. All right. So for sulfuric acid, it's 98.08. So that will go here. Grams of sulfuric acid. So that this will cancel out with that. And then the next conversion factor now is to find the mass of the solution. And that is given by this number right here, because the 65% sulfuric acid means that for every 100 grams of the solution, 65 grams of it would be sulfuric acid. And the way we will represent that here is that we're going to put 65 grams of H2SO4 down here. S4. And up here, I'm going to put 100 grams of the same, of the solution, sorry. All right. So that this will cancel out with that. And then now we get to the very last conversion factor, because again, let me remind you, we're trying to define the milliliters. So how do we get from grams of solution to the milliliters of solution? And the answer is right here, the density, right? So the way we would represent that here is that I'm going to put 1 mil above of the solution. And down here, I'm going to put 1.55 grams of the solution. So that this goes with that. And then we have to do the number correction. So let's do that. So, and again, please folks, make sure that I'm doing the right thing by doing the calculation along with me, just in case I made an error somewhere. So 1000 divided by 132.14, and then multiply by 90.08, and then multiply by 100, divided by 65, divided by 1.55, And according to my calculations, I got, now in this case, I have to round off to. I round off to 2 sig because of the 65 here. So according to my calculation, this would be equal to 740 mils of solution. And that's how that is done. All right, any questions? Any questions? No questions? Any questions out there in Zoom? Okay, so let me go back to the PowerPoint here and continue our discussion by looking at, again, another topic that you should have encountered in your introductory high school chemistry, whatever, right? Limiting reactants, right? So basically, this concept is important when you have a situation where you have a reaction which involves more than one reactant. And what you'll find is that in some cases, even though the equation might suggest a proportionality in terms of the amount of reactants that you're going to need in order for the reaction to take place, what you'll find in practice is that in order to ensure the reaction actually progresses sufficiently to produce products, you need to have one or more of the reactants in excess of the other, right? So, and that's just a practical aspect of carrying out chemical reactions. So even though the equation might say, for example, you need 2-to-1 mole ratio between A and B, in actual practice, you probably need a greater ratio of, let's say, 3-to-1, between A and B in order for the reaction to take place, right? So that's the reason why this concept of limiting reactant is important, right? So as stated here, many reactions are carried out with a limited amount of one reactant and an excess of the other reactant, right? So the reactant that is completely used up under those circumstances, we call that the limiting reactant, right? And that limiting reactant is basically what determines the product outcome in terms of how much product you expect to get, all right? So another key thing here, which is very important, the limiting reactant is not necessarily the one present in smallest amount. That's a very common error that some people tend to make or think that, okay, if one is in a smaller amount than the other in terms of reactants, then the smaller amount will be the limiting reactant. That's not the case. We're going to go into at least one example to show you how the limiting reactant is okay. Now, we're going to use this analogy here to try to explain. It's not a chemistry example, obviously, but it can be useful in terms of understanding and explaining this whole concept of limiting reactant. So let's say you are responsible for making packaged meals for some event, maybe a picnic, whatever. And this is a combination of items that you're going to need in order to make one packaged meal, right? You're going to need one sandwich, 2 cookies, 1 orange, right? So there's a 1-to-2-to-1 ratio between the sandwich, cookies, and orange to make one packaged meal, right? So here's the situation here. Let's say we have 10 sandwiches at hand. We have 18 cookies and 12 oranges. So the question is, how many packaged meals can you make out of these items as they're listed here, right? Now, if you look at things from the standpoint of the 10 sandwiches, given this equation here, right? According to this equation here, the 10 sandwiches would require 20 cookies, right? Because of the 1-to-2 ratio between them. But we do not have 20 cookies. We have what? 18 cookies, right? So therefore, that would not work in terms of using up all the sandwiches to combine with the cookies, right? Now, if you look at things from the standpoint of the oranges, all right, a 1-to-2 ratio exists between the orange and the cookies. So for 12 oranges, you're going to need 24 cookies. Again, you don't have 24 cookies, right? So therefore, that won't work either in terms of using up all the oranges. Now, if you look at things from the standpoint of the cookies, right? Now, remember, there's a 2-to-1 ratio here, 2-to-1 ratio here, right? So as far as the 18 cookies are concerned, right? Based on this relationship, 18 cookies would require 9 sandwiches, right? We have 10 sandwiches. So therefore, we have more than enough sandwiches to use up all the cookies, right? Which means that there will be 1 sandwich left over, right? And then if you look at the relationship between cookies and oranges, again, it's a 2-to-1 ratio. Again, 2 cookies would require, 18 cookies would require 9 oranges. We have 12 oranges, so we have more than enough oranges to use up all the cookies. You're going to have 3 oranges left over, right? So in this particular situation, it's not a chemistry situation, as I said before, but it relates in terms of what we're talking about. So in this particular situation, the cookies would be analogous to the limiting reactants, right? The cookies would be the limiting item, okay? And it is the cookies that will determine how many packaged meals you can make out of what we have here, right? So basically, let me just write something down here. Initially, we would have 10 sandwiches. So this is initial, right? Initial, right? 10 sandwiches, 18 cookies, and 12 oranges, right? And then basically, we're going to use up all the 18 cookies, right? Right? So therefore, there'll be none left. Now, over here, you'll be using up 9 oranges. So you're going to have 3 left. And over here, you'll be using 9 sandwiches. So you're going to have 10 left, right? I'm sorry, 1 left. All right. So therefore, the cookies will be the limiting item. And the oranges would be in excess as well as the sandwiches or the 1 sandwich, right? So basically, this illustrates the limiting item concept in that the limiting item is the one that will be completely used up. And not only that, as I said before, is going to determine the amount of packaged meal. So initially, you'd have no packaged meal, and now because of the limiting item, which will be completely used up, you're going to have 9 packaged meals produced, and therefore 9 packaged meals would be the possibility in terms of how many of those you can make from the items that are given. All right. So that's basically what happens in this case, and we can apply it to chemical reactions if you're given the amounts of reactants and so on. Okay. Any questions about this before we move on? Any questions? Any questions? So the next slide has a real chemistry example of this, right? Now, what is represented here is a reaction between a compound, a gas known as ethylene, C2H4, plus bromine, and the product of that reaction is dibromoethylene, 1,2-dibromoethane, I'm sorry, and that has the formula of C2H4Br. Now, Br2. Now, in this particular case, it's made easy for us to understand because it's a 1-to-1 mole ratio between the ethylene, the bromine, and the final product, right? Now, so therefore, what this is telling you is that 1 mole of this will react with 1 mole of that to give you 1 mole of that, right? Now, in this particular case, we have 1.0 moles of the ethylene, right? I'm going to put 1.0 moles of the ethylene here initially. And as far as the bromine is concerned, we have 0.80 moles of bromine. And initially, we would have none of that, right? Now, because it's a 1-to-1 mole ratio, we can easily tell which of the 2 reactants would be the limiting reactant. And that would be bromine, right? Because you have 0.8 here and you have 1.0 moles here. And you know it's a 1-to-1 mole ratio between those 2, right? So we can easily predict that all of the bromine will react, right? So you're going to have none left. Now, because 0.80 moles of the bromine reacts, that means that the amount of ethylene that reacts is also 0.80, right? So basically what will be left would be 0.20 moles, right? And then over here, because of the 1-to-1 mole ratio between the bromine and the 1,2-dibromoethane, we can say that the amount of that product produced would be plus 0.80 moles, which means that you're going to end up with 0.80 moles of the product, right? So after the reaction is completed, after the limiting reactant is used up, you're going to have only 2 substances left behind. You're going to have 0.8 moles of the product, and you're going to have the leftover ethylene remaining, right? So in this particular case, the bromine, I'm going to squeeze this. The bromine would be the limiting item, the limiting reactant, right? And the ethylene would be the excess reactant. All right? And therefore, it is the bromine being the limiting reactant that will determine the amount of product that you expect to get, which would be, in this case, 0.80 moles, right? So that's a real example of this. Now you'll notice that the bromine is 128 grams, right? In terms of being equal to 0.80 moles, while the ethylene is 28 grams, right? So you can see here that the bromine is a limiting reactant, even though the mass is greater, which underscores what I said earlier. You cannot just look at the masses and tell which is limiting, right? You have to look at the equation, you have to look at the stoichiometry of the equation, and you have to look at the moles of the reactants that are there before you can make any assessment as to which one is limiting, right? So don't look at the masses. You have to look at the limited, you have to look at the equation, look at the moles, determine which one is limiting based on that, and then you can go from there. No, I think there's a question. Oh, okay. So it says here, a couple of questions here. Why is ethylene left over? Well, we talked about that. What mass of ethylene is left over? Oh, so they're asking for the mass. We know that the moles is that. So how would you determine the mass for ethylene that is left over? How would you determine the mass of ethylene that is left over? Let me see if I can.
You can set up a conversion of moles to grams.
Okay, so I'm going to do it right here. 0.20 moles of C2H4. And what do we multiply that by? What goes down here as a denominator? This should be easy, guys. You're going from moles to grams.
I think you want to start by it's in NV.
Give me the molar mass.
Yes.
All right, so again, I'm feeling lazy today, so I'm going to go back to the calculator. So in this case here, C2H4, 28.05. All right, so here I'm going to put 28.05 grams over 1 mole. So 0.2 times 28.05. So according to my calculation, rounded off to 2 sig figs, that would be 5.6 grams. So that would be the amount of the ethylene that is left over at the end of this reaction, right? Okay, so this is a relatively simple example of a limiting reactant type problem, primarily because of the 1-to-1 mole ratio. Now things become a bit more complicated when you have, a different situation like a 3-to-2 mole ratio between the reactants and so on. So let me just go through this slide here to talk about recognizing and solving limiting reactant problems. These are the problems where you have 2 or more reactants. If you have only 1 reactant, then that reactant is a limiting reactant, right? But if you have 2 or more reactants, then you have to determine which is which, right? Which is limiting and which is in excess. So there are a couple of approaches you can take. You look in different textbooks here, you'll see different approaches. This is the one that I prefer, right? So basically what you're going to do is start out with the amount of each reactant present in the beginning and determine how much product you expect to get based on each reactant, right? And the one that on paper produces the lowest amount of product, that would be the limiting reactant based on that type of calculation, all right? So to illustrate this, another example here, let me copy and paste this word. And this is a very typical limiting reactant problem. Okay, so let me okay, so the question says magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. And it's a 2-part question. The A part is saying how many grams of magnesium nitride can be made in the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen. So that's the A part. The B part is asking how many grams of the excess reactant remain after the reaction. Okay, so let's start off with the A part. So what's the first thing you would do in order to answer this question? Anybody? What's the very first thing you would do to answer this question? Okay, the equation. So what are the reactants? Based on the information provided. Magnesium and what? Hydrogen? Nitrogen. What's the formula for nitrogen gas? Hmm? No. You were in my class last semester, right? My introductory class, right?
Yes.
Do you remember me telling you guys that there are 7 elements that exist as diatomic molecules?
Yes, I thought so. They
Is it
all
N2?
Right, the formula is N2. Folks, please remember this. I think I told you guys this earlier, but just in case I have. There are 7 elements that exist as diatomics, right? Nitrogen, oxygen, hydrogen, and chlorine, bromine, and iodine, and chlorine. All right? Those exist as diatomic molecules, meaning that there are 2 atoms per molecule, right? So if you see a question like this and it says nitrogen reacts with whatever, then you should immediately remember that nitrogen exists as N2. All right? So now the next question is, what will be the product? And here's a formula, here's the name of the product, I'm sorry. So what's the formula for magnesium nitride? And let me give you a hint, that table that I gave you, which lists the ions, you should find that helpful in determining the formula. Not the periodic table, the list of ions. The list of common ions. The formula, or I should say the name, is magnesium nitride. What's the formula for the magnesium ion? Let's start off with that first. What's the formula for the magnesium ion? Mg what? What's the charge?
2+.
2 plus, exactly. What's the formula for the nitride ion?
And
And what?
is it 3
And 3 minus. Okay, so how do we combine these to get the formula for magnesium nitride? You're going to need 2 of these and, I'm sorry, you're going to need 3 of these and 2 of these. So the formula for magnesium nitride will be Mg3 and 2. So that's what we're going to put here, Mg3 and 2. So very important, folks, that you are able to write down the formulas for, different substances based on information provided in the question. So now that we have this unbalanced equation, now we have to balance it. So how do we go about balancing it?
You would put a 3 in front of the Mg.
With a 3 in front of the Mg, and that's all you need, right?
Already have an N2.
Because the 2 nitrogens are balanced already. Okay, very good. So this is basically what you need to do for every type of stoichiometric problem. You need to have a balanced equation before you can get to the math problem, right? Now, the question is asking for how many grams of magnesium nitride that can be made in a reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen. So as I said before, the way I'm going to show you, if you look in different textbooks, you'll see different methods. But the way I'm going to show you is that you're going to start off with each reactant and determine, based on each reactant amount, how much of the product you expect to get. So in this particular case, I'm going to start off with the 35.00 grams of magnesium, and then I'm going to convert that to moles. So the next conversion, or the first conversion factor, is 1 mole of magnesium. And if I'm not mistaken, the molar mass of magnesium is 24.31 grams, all right? So this will go with that. The next step is to look at the mole ratio between the magnesium and the magnesium nitride. So there's a 1 here, right? So I would represent that in the next conversion factor by putting 1 mole of Mg3N2, and down here I'll put 3 moles of Mg, and then I'll work this out. So 3.5 divided by 24.31, and then divide by 3, and according to my calculation, I got 0.4799 moles of Mg3N2, all right? So that's based on the mass of magnesium given. I'm going to do something similar, but this time I'm going to start off with the nitrogen, 15.0 grams of N2, right? So I'm going to first convert to moles. You're going to have 1 mole of nitrogen, and then the molar mass of nitrogen is, because it's N2, that'll be 2 times 14.01, which would be 28.02 grams of nitrogen. So that this will go with this, and then the next step will be the conversion factor, which relates the moles of nitrogen to the moles of the product, right? And that's a 1-to-1 mole ratio. So I'm going to put 1 mole of Mg3N2 above and 1 mole of N2 below. And then we do the calculation. So that would be 15 divided by 28.02 times 1. So I got 0.5353 moles of magnesium nitride, all right? So the next step is to compare these two. Compare these two numbers. And the one that's lower would be this one right here, right? Which means that the magnesium is the limiting reactant, right? So what I would do now, because the question is asking how many grams of the product, I'm going to take this number here. So mass of magnesium nitride. I'm going to take this number, which is 0.4799 moles, and multiply by the molar mass of magnesium nitride. So I'm going to go against my calculator here. And according to this, it's 100.93. So 100.93 grams of Mg3N2 over 1 mole of Mg3N2. It should be Mg3N2. And let's see what I give. So that would be 0.4799 times 100.93. And according to my calculation, this works out to be equal to 48.44 grams of Mg3N2. And that's how the A part is done. All right? Any questions about this? Any questions? Any questions? Okay, so that's the A part. Is it okay for me to clear this? All right, we do that. Oh, you know what? Before I clear this, let me see here. The question is asking how many grams of the excess reactants remain. I'm going to need, you know what? Let me scroll down. Let me not clear this. Let me scroll down because I'm going to need some information from the A part. So this here is A part. So I'm going to continue with the B part here. Now the B part is asking how many grams of the excess reactant remain after the reaction. So now that we know which is the limiting reactant, right, which is the magnesium, that means that the nitrogen would be the excess reactant, right? So we need to find out how much nitrogen remains after the reaction is completed, right? Now, how are you going to do that? Well, what we need to do, since we know that the magnesium is a limiting reactant, what we can do is use the mass of the magnesium to find out how much of the nitrogen that will react with it. So what I'm going to do is start off with the 35.00 grams of the magnesium. I'm going to convert that to moles. 1 mole of magnesium above and 24.31 grams of magnesium above. And then the mole ratio, this time we're gonna look at the mole ratio between the magnesium and the nitrogen. That's a 1 to 3 mole ratio. So I'm gonna put 1 mole of nitrogen here and 3 moles of magnesium down here. And then the last step in this series is where I convert the mole of nitrogen to grams. And we saw that the molar mass of nitrogen is 28.02 grams of nitrogen, right? So let's see what that gives. 35 divided by 24.31 divided by 3 times 28.02. And according to my calculation, this works out to be rounded off to 4 sig figs. That would be 13.45. 13.45 grams of nitrogen. Now remember, this is the mass of nitrogen that reacted, right? What the question is asking for is the mass of the nitrogen that remains, right? So how do we find the mass of the nitrogen that remains? Anybody? So mass of N2 remaining, that's what we're trying to find. How do we find the mass of nitrogen remaining? This is the amount that reacted. Anybody? How about you guys out there in Zoom? If this is the amount of nitrogen that reacted, how do we find the amount of nitrogen that remains? Yes, ma'am. Okay, and what was the given amount? 15.00 grams of nitrogen that was given. And we're going to subtract from that 13.45 grams. And you're correct. 15 minus 13.45. So the answer is 1.55 grams of nitrogen remaining. All right. Any question about this one? Any questions? Questions? Okay. Going back to the PowerPoint. So let's see what's next. Okay, so another concept, again, you should have met this before. Talking about the yield of chemical reaction. Now, in a perfect world, right? Whatever the amount that you expect to get based on calculation that we have done before, right? Is what you would get. But of course, we know that would not be so because we don't live in a perfect world. Very often what you'll find is that the amount of product you expect to get would be different from what you actually get, right? What you actually get very often is less than what you expect to get in terms of the product outcome, right? And there's several reasons for this, right? For example, you could have a situation where the product that is formed itself reacts to form other products, right? So therefore you won't be able to determine, or you won't be able to get the maximum possible amount of product. Another reason is that the product that is formed will go back and form the reactants. In other words, it's a reversible reaction, right? So that's another reason, all right? And there are other reasons which I won't get into right now. So at this juncture, because of that, it's very important that you understand the difference between what is called the theoretical yield and what is called the actual yield, right? The theoretical yield is the amount of product that you expect to get based on the limited reactant, right? So like the example that we just looked at, the amount of product you expect to get, that would be the theoretical yield. In a perfect world, that's what you'd expect to get. The actual yield, as the term suggests, is the amount of product that you get when you do the experiment, isolate the product and weigh, right? That's the actual yield, right? And what you'll find is that the actual yield is very often less than the theoretical yield, all right? In fact, if you get a reaction where the actual yield is within, I would say 80%, you're doing very good in terms of product outcome, all right? So in order to get a measure of how successful a reaction is based on comparison between the actual and the theoretical yield, we have what is known as the percent yield, right? And this is the formula for calculating the percent yield. Percent yield for reaction is the actual yield divided by the theoretical yield times 100%, all right? So this is used very often. If you look at any chemical literature, and I'm talking like, you know, journals where people do research and produce their findings, right? And if their research involves making compounds, one of the things that they would mention or quote is the percent yield of the reaction that they conduct. That is basically what is expected when in chemistry when you're doing synthetic work. All right. Okay. So here's an example: the reaction between zinc and sulfur to form zinc sulfide. Right. So this is an example of why is it that you won't get 100% yield when it comes to most chemical reaction. So you mix the two together, you heat it together, and then you look at the product outcome. And this is what happens. You're trying to do this reaction here: zinc plus sulfur to form zinc sulfide. This is what you're trying to achieve, right? But what happens? Not only will you get the product that you want, but you get some other product. For example, you get zinc oxide because some of the zinc will react with oxygen to form zinc oxide, right? Also, some of the zinc itself may not react, right? So you have unreacted zinc in a mixture, right? And then there's some other impurities that may exist. So for all these reasons, you're going to end up with a less than 100% yield. And that's a very simple reaction where this happens. So even for more complex reactions, you're going to see that to be true as well. All right. Okay. Okay, you know what? Let me not do that. Okay, so let's talk about solutions. And for those of you enrolled in my lab, we just did an exercise which is part of what we're going to discuss here, dealing with molarity and dilution and all that good stuff, right? So let's talk about what we mean by a solution. A solution, of course, we know is a homogeneous mixture of two or more substances, and there are two main parts to any solution. You have what is known as the solute and what is known as the solvent, right? And broad definitions here: solute is basically the substance which is being dissolved, while the solvent is the substance that is doing the dissolving. Now, typically, if you have a solid dissolved in a liquid, then the solid is the solute, the liquid will be the solvent. However, if you have two liquids, if you have one liquid added to another liquid, the one that is determined to be the solute is the one in lesser amount, right? While the solvent would be the one in greater amount, all right? So those are usually the type of solutions that we're talking about here, all right? Now, let's talk about the concentration of a solution. The concentration of a solution is basically a ratio between the quantity of solute and the quantity of either the solvent or solution. Now, there are different ways of expressing those quantities, right? The one that we'll be talking about here in this particular chapter is that the quantity of the solute would be expressed in moles, while the quantity of the solution will be expressed in liters, right? So as stated here, you can have a solution which is very concentrated, and you can have one that is very dilute. Basically, those terms are relative terms. So, of course, we have to have a more quantitative way of expressing concentration, and that leads us to what is called the molar concentration, which is just one way of expressing the concentration of a solution. There are other ways as well, which we won't get into in this particular course, but in Chem 2, you'll be discussing more about that, all right? So this is the definition of molarity: moles of solute divided by liters of solution. And therefore, as I said to my lab group this past week or this week, the units of molarity is dependent on the units over here. So this is moles, and the units here is liters. So therefore, we can express the unit of molarity as moles per liter, or you can simply use uppercase M, all right? So uppercase M is the same as moles per liter, all right? So that's the unit of, that's one unit of concentration, all right? So for example, if you see something like this, 0.35 M, right? To express the molarity of a solution, you should understand what that means. That means that for every liter of that solution, the amount of moles of solute is 0.35 moles, all right? And remember, and this is very important, down here is the liters of solution, not liters of solvent, right? Okay, so let's see what happens next. So how do we make solution of a particular concentration? Those of you enrolled in my lab just experienced this, right? You're going to need a couple of things. You're going to need to determine the final volume of the solution that you're trying to make, right? And based on that, and based on the molarity of the solution that you're trying to make, you can determine how much of the solute that you're going to need. So in this particular case, we use this piece of glassware known as a volumetric flask, right? This is made very accurately, and they're designed to measure specifically a particular volume accurately, right? And they come in different sizes. The smallest one I've seen is a 10 ml volumetric flask, and the largest one I've seen is a 2-liter flask, all right? This one is a 1-liter flask, right? And if you look, well, I don't know if you can see from where you are, but there's a mark that is etched right here that represents the particular volume, right? So if you add liquid up to that mark, if the bottom of the meniscus is at that mark, then you know that you have 1 liter of the liquid inside that flask, all right? So basically, to make this solution, what you'd have to do is do some calculations to determine the mass of the solute. Now, in this case, the solute is potassium permanganate, right? So you have to do your calculations based on the final volume of the solution and the concentration that you're trying to achieve. And based on your calculation, you're going to end up with a mass of 1.580 grams that you need to weigh. So that's what this person did. He or she weighed the, this looks like a man's hand, so I'm going to say he, all right? So you're going to weigh 1.580 grams of the compound. And then what you should do, which is not quite shown here, is that you add the solid first to the flask, right? And then you add water to about half or 1/3 full of the flask. You stopper it, shake it up to make sure that the solution is homogeneous. And then you just continue to add water until the meniscus gets up to the mark. And then you stopper it, shake it up again to make sure it's homogeneous. And that's basically how you make your solution, starting from scratch, from the actual solute, which is the potassium permanganate in this case, right? And that's basically it, all right? That's how you make a solution accurately, or as accurately as you can, of a particular solid, all right? Okay, so that's basically how that is done. So let's see if we can do, what time is it?
120.
Okay, should be able to do a couple of these. So let me copy this. Paste it here. Okay, so this question is asking, what is the molarity of the solution in which 333 grams of potassium hydrogen carbonate is dissolved in enough water to make a 10-liter solution? So let me hear your ideas about this one. You guys should be able to do this one. They gave you the mass of the potassium hydrogen carbonate, and they gave you the volume of the water. Now remember, molarity, which is what the question is asking for, is equal to moles of solute divided by volume of solution in liters. All right? So, how would we, in this case, for this question, determine the molarity? Okay, we need to find the molar mass of potassium hydrogen carbonate, right? Which means we need a formula for potassium hydrogen carbonate, right? So what's the formula for potassium hydrogen carbonate? Anybody? Yes, ma'am. KHCO3, all right? So again, I'm going to use my calculator here to find the molar mass of carbonate, of potassium carbonate. Oops. And let's see what I get. Okay, so according to this, it's 100.12 grams. So, so molar mass here is 100 0.12 grams per mole, all right? Okay, so what next? Now that we have the molar mass, divide this by 100.12 grams. Oh, I'm sorry. It's the other way around. Yeah, 100.12 goes below. And 1 mole goes above, right? So that gives you the mole, and then we divide that by 10.0 liters. That's it. So let's see what this gives. 333 divided by 100.12 divided by 10. So according to my calculation, this works out to, when rounded up to 368, 0.333 M. That's all that is done. All right? Any questions about this? Questions? Okay, let me go back to see what the next question is. Okay, so the next question is, I want to just copy and paste. Let me just copy and paste it right here. And let me also get rid of this here. Okay, so we want to prepare a 6.68 molar solution of sodium hydroxide. So the A part is asking how many moles are required to prepare 0.50 liters of 6.68 moles M sodium hydroxide. So how would you answer that question? They're asking for the moles, they gave you the volume, and they gave you the molarity, which is moles per liter. So how would you answer that question?
You do, so we're looking for moles, right?
I'm sorry?
We're looking for moles, right?
Yes, sir. We're looking for moles of sodium hydroxide.
So we have the molar.
We have the molarity and we have the volume
So in liters,
in liters.
then you would do molarity times 5 liters.
Exactly. So 0.50 liters multiplied by 6.68 moles per liter. So this cancels with that. So this gives you 3.34 moles. All right, that's it. Okay, now B is asking for the volume in liters. They gave you the molarity, it's the same molarity as above. And they're asking for, oh, and they also gave you 2.35 kilograms of sodium hydroxide. So in this case, they're asking for the volume in liters. So let me hear your ideas about this one. Excuse me. How would you solve this problem? They gave you the mass of the sodium hydroxide in kilograms, and they also gave you the molarity of the solution, which is the same as the one before. And they're asking for the volume in liters. Yes, ma'am.
Figure out how many moles of this, compound that we have,
Okay, so how would you do that?
convert from kilograms to grams.
Okay, so 2.35 grams, I'm sorry, kilograms. You're going to convert to grams. So you're going to have 1 kilogram up below and 1,000 grams above. All right. And then what?
Divide that by the mole.
Okay, so you're going to have 1 mole of sodium hydroxide and the molar mass. Now that one, if I remember correctly, is about 40.00 grams. All right. So this will cancel with that. That will cancel with that. And then what? So far we have the moles, and the question is asking for the liters, right? So what would you multiply that by to get the liters? I'm sorry? Well, you won't multiply by the molarity, you'll divide by the molarity, because remember, you're trying to find the liters, so it will be 1 liter above and the 6.68 moles below. Let's see what that gives. So that is 2.35 times 1,000 divided by 14.00 and then divided by 6.68. And according to my calculation, this works out to be equal to 368. So that will be 8.79 liters. That's how you do that. All right. Any questions about this? Any questions? Questions? Okay, going back to the PowerPoint. One more question. This one is interesting. And then we'll get this here. Okay, so let's look at this question. It says you have a stock bottle of aqueous ammonia. It is 28% ammonia by mass. So what that means is that for every 100 grams of the solution, 28.0% of it would be pure ammonia, right? They also gave it a density and they're asking for the molarity of this solution, right? Okay, so how would we do this? Okay, I would take the approach that, well, going back to the definition of molarity, right? The definition of molarity is moles per liter, right? So if you can find out or calculate the amount of moles in 1 liter, right? Then that would give you the value of moles and that would be the molarity. So what I'm going to do here is start off with 1 liter of solution. All right. And what I would do is convert that to volume. All right. So I'm sorry, to milliliters. So I'm going to have 1 liter of solution here. And above, I'm going to have 1,000 mils of solution. All right. Now, the next step is to find out the mass of the solution, right? And this is what you're going to use in this conversion factor, right? Because this is the density, which is mass per volume, right? Or grams per milliliter, right? So the way I would express that here is 0.898 grams for every 1 milliliter of solution, right? Solution here as well. So this will cancel out with this will cancel out with that. So up to this point, we have the mass of the solution. Now here is where we go from the mass of the solution to the mass of ammonia. This is what we're going to use. Remember the 28.0% is the mass of ammonia per 100 grams of the solution. So the way I'm going to represent that here is that I'm going to put 100 grams of solution here. And I'm going to put 28.0 grams of ammonia up top. All right. Excuse me. But we're not finished yet because remember, we're trying to find the moles in 1 liter. Up to now, we have found the grams in 1 liter. So the next step would be the molar mass. Dividing the mass in grams. Oh, by the way, this cancels out with that. So we're going to put the molar mass in this conversion factor, right? And the way we're going to do it is that we're going to put 17.03 grams of ammonia for every 1 mole of ammonia, right? So the 17.03 is the molar mass of ammonia. Actually, it's all the way around. My bad. It should be 1 mole of top. And 17.03 grams of ammonia below. All right. So this will cancel out with this, and that will give us the moles. So 1,000 times 0.898 times 28.02 divided by 100 divided by 17.03, and the answer I got is 14.8 rounded off to 368 moles, right? So this is the moles of ammonia in 1 liter of the solution. So therefore, we say that the molarity is equal to 14.8 M. And that's how you do that, right? Okay, any questions about this? Any questions? Questions? All right, going back to the PowerPoint. Okay, so we're done with these questions on this page. All right, so I think this is gonna be the last we're gonna talk about, and then we'll call it. So again, for those of you enrolled in my lab, we had some experience with this, dilution of solutions. As I said to the lab group, this is a very common practice in labs all over, not only chemistry, but biology and so on, where solutions may be needed to, you may need to make solutions. Now, you can make your solutions from scratch, as we said before, starting with the solute and the solvent. But very often what you find is that you may have an experiment which calls for solutions of a particular molarity, but you don't have that solution in your stock room. You have more concentrated solution of the same solvent, right? So basically what you have to do is ensure that you add the right amount of solvent to a given amount of that solution to get your new solution of a new molarity. So basically you have to dilute, which is basically just simply adding your solvent to increase the volume. And basically, as I said again to the group, to the lab group, when you add your solvent, you're not changing the amount of solute, you're changing the volume, right? So therefore, the concentration will decrease, right? So here's an example. We have here a solution of 0.0050 moles of iodine in a 0.10 liter solution, and the resulting molarity of that solution is 0.050 m, right? Now, if you were to add more solvent to it, so that the volume increases from 0.10 to 0.50, there will be a corresponding fall in the molarity, right? So basically, you're increasing the volume fivefold, and you will also at the same time decreasing the concentration fivefold, right? And this is just giving you a pictorial representation of what's happening here. Basically, the relative amount of the solute molecules to the solvent molecule to the solid molecules will increase as you go from the more concentrated solution to the more dilute solution. All right. So remember, the amount of solute does not change, as you can see here. The moles of iodine remains the same. It's the volume that you're changing, and therefore the molarity as a result will increase. And the way to relate the initial and final concentration and volumes is very easy. It's based on the fact that the moles of the solute doesn't change, which means that the molarity times the volume is a constant, right? So therefore, we can represent the relationship between the concentrated and the concentration and the volume of the more concentrated solution to the same terms for the more dilute solution. Personally speaking, I prefer to use C1 V1 is equal to C2 V2, right? C1 and V1 would be the initial concentration and volumes. C2 and V2 would be the final concentration and volume, right? Okay, and this is going to be the very last thing we're going to talk about here. So here is basically how this is done in practice. Again, those of you who had as like me would know how to do this. This question is asking how many milliliters of 2.00 m copper 2 sulfate stock solution are needed to prepare 0.250 liters of a 0.400 m CuSO4 solution, right? Very easy. All you have to do is identify what is C1, what is C2, what is and so on, right? So since this is the initial concentration, I'm going to call that C1. So this is C1 here. This here would be C2, and this here would be V2, right? So to find V2, which is what the question is asking for, that would be equal to C, I'm sorry, question is asking for V1. So therefore, V1 will be equal to C2 V2 over M1 over C1, I'm sorry. So basically, it's going to be 0.400 M multiplied by V2, which is 0.250 liters, divided by C1, which is 2.00 M, and that will give you V1. But remember now, the question is asking for the volume in milliliters. So we have to do some conversion here. 1 liter there, 1,000 mils above. And let's see what that gives. 0.4 times 0.250 times 1,000. And then divide all of that by 2. Oops, okay, I made a mistake. 0.4 times 0.250 times 1,000. Okay, and then divide by 2. Wow. So I got rounded off to 3 sig figs, 50.0 mils. All right? And that's basically how that is done. All right. I'm gonna stop here. Let me just get those persons who came in late. And then that's it for today. Francois, let me just check here. Is Francois here? It's not. Malberg. It's not. Martin. It's not. Perouche is here. Simmons. And White. Okay. That's it, folks. So remember your test is next week. I posted the answer keys for both assignments 1 and 2. So you can review those. And again, if you have any questions, please feel free to contact me, all right? Yes, sir. And for you guys out there